Welcome to ReLU Radio, the podcast where we unpack the latest and greatest in machine learning research. I'm your host, Adam, and today we're diving into a fascinating paper titled Diffusion Policy, Visuomotor Policy Learning via Action Diffusion, from researchers at Columbia University, MIT, and Toyota Research Institute. Joining me to break it all down is my co-host, Eliza. Welcome, Eliza.
Thanks, Adam. I'm excited to discuss this paper. It presents a really intriguing new approach to robot learning.
Absolutely. Let's start with the core concept. In a nutshell, this paper introduces something called diffusion policy, a new way of generating robot behavior by representing a robot's policy as a conditional denoising diffusion process. Eliza, can you break down what that means in simpler terms?
Sure thing, Adam. Imagine you're trying to teach a robot how to perform a task, like picking up a mug. Traditionally, we might directly tell the robot, move your arm like this, then grasp like that. But with diffusion policy, it's more like we're giving the robot a blurry, noisy picture of the right action, and then teaching it how to gradually sharpen and refine that picture into the correct movement. It's a bit like those AI image generation models, but for robot actions instead of pictures.
That's a great analogy. Now, the paper mentions that this approach consistently outperforms existing state-of-the-art robot learning methods. What makes it so effective?
Well, there are a few key advantages. First, diffusion policy is really good at handling situations where there might be multiple correct ways to do a task, what we call multimodal action distributions in ML speak. It's also well-suited for high-dimensional action spaces, which is crucial for complex robot movements. And perhaps most importantly, it's remarkably stable during training, which has been a major challenge for other approaches.
Fascinating. Let's dive a bit deeper into how this actually works. The paper talks about denoising diffusion probabilistic models, or DDPMs. Can you explain what these are and how they're applied here?
Absolutely. DDPMs are a type of generative model that work by gradually denoising random noise into meaningful data. In the context of diffusion policy, we start with random noise and iteratively refine it into a useful robot action. The magic happens in the denoising process. The policy learns to predict and remove the noise step by step until we're left with a clean, precise action.
It's almost like the policy is playing a game of hot and cold with itself, gradually getting warmer until it finds the right action. How does the training process work for this?
That's a great way to think about it, Adam. The training process is actually quite clever. We start with examples of correct actions from our dataset. Then, we add random noise to these actions and ask our model to predict what that noise was. By learning to predict the noise, the model implicitly learns how to denoise, or in other words, how to generate the right actions.
Interesting. Now, the paper mentions that they've adapted this approach specifically for visuomotor policy learning. What changes did they make to make this work for robots?
Great question. They made two major modifications. First, they changed the output to represent robot actions instead of, say, image pixels. Second, and this is crucial, they made the denoising process conditional on visual observations. So the robot can look at its environment and use that information to guide its action generation.
That makes sense. They also talk about using this for closed-loop action sequences. What does that mean in this context?
This is a really cool part. Instead of just predicting one action at a time, the diffusion policy can predict a whole sequence of actions. But here's the key. It doesn't just blindly execute that whole sequence. Instead, it predicts a sequence, executes a small part of it, then looks at the world again and replans. This allows for both consistent, smooth actions and the ability to quickly react to changes or unexpected events.
Wow, that's pretty impressive. It's like the robot is constantly thinking a few steps ahead, but still staying flexible. Now let's talk about some of the key design decisions they made. The paper mentions a few different network architecture options, Can you break those down for us?
Sure thing. They explored two main types of neural network architectures: convolutional neural networks, CNNs, and transformers. The CNN-based approach worked well for most tasks right out of the box, without much need for tuning. However, they found that for tasks requiring quick, sharp changes in action, a new architecture they call the time series diffusion transformer performed better.
Interesting. And what about the visual part? How does the robot actually see the world?
They use a pretty standard approach here, our RESNET 18 architecture for processing images. But they made some tweaks, like using spatial softmax pooling to maintain spatial information and replacing batch norm with group norm for more stable training. The visual information is then used to condition the action generation process.
Got it. Now, one thing that caught my eye was the mention of accelerating inference for real-time control. That sounds important for actually using this on real robots. Can you explain what they did there?
Absolutely. This is crucial for practical applications. They used a technique called denoising diffusion implicit models, DDIM, that allows them to use fewer denoising steps during inference than during training. In their real-world experiments, they were able to get the inference time down to 0.1 seconds on a standard GPU, which is fast enough for real-time robot control.
That's impressive. Now, let's talk about some of the interesting properties of diffusion policy. One thing they highlight is its ability to model multimodal action distributions. Can you explain what that means and why it's important?
Of course, multimodal distributions basically mean that for a given situation, there might be multiple correct actions. Think about picking up a mug. You could grab it from the left side or the right side, and both would be valid. Traditional methods often struggle with this and tend to average out these options, resulting in an action that doesn't make sense, like trying to grab the mug from the middle. Diffusion policy, on the other hand, can represent and choose between these multiple valid options.
That makes a lot of sense. They also mentioned something about a synergy with position control. What's that about?
This was actually a surprising finding. Most recent work in robot learning has used velocity control, where you tell the robot how fast to move in each direction. But they found that diffusion policy works better with position control, where you directly specify where the robot should move to. This is interesting because position control is generally considered harder to learn, but diffusion policy seems to handle it well.
Fascinating. Now, let's talk about their evaluation. They tested this on quite a few tasks, both in simulation and in the real world. What were some of the key findings?
The results were pretty impressive. They tested diffusion policy on 15 different tasks across 4 benchmarks, including both simulated and real-world environments. The tasks ranged from simple object manipulation to complex bimanual tasks like folding shirts. Across the board, diffusion policy outperformed existing methods, with an average improvement of 46.9%.
Wow, that's a significant improvement. Can you give us an example of one of the real-world tasks they tested?
Sure. One interesting task was called Push T, where the robot had to push a T-shaped block into a target area and then move its arm to an end zone. This task is tricky because it requires precise movements and has multiple stages. Diffusion policy achieved a 95% success rate on this task, compared to 0% and 20% for the best-performing baseline methods.
That's incredible. They also did some bimanual tasks requiring 2 robot arms. Can you tell us about one of those?
Absolutely. One of the most impressive bimanual tasks was shirt folding. This is a complex task that requires up to 9 discrete steps, including grasping sleeves, folding them, and then folding the shirt in half. It's particularly challenging because the 2 arms need to work in close coordination. Diffusion policy achieved a 75% success rate on this task, which is really impressive given how difficult it is even for humans to fold shirts consistently.
As someone who still struggles to fold shirts neatly, I'm both impressed and a little worried about my future job prospects. Now, as we wrap up, what do you see as the main limitations or areas for future work in this approach?
While diffusion policy shows a lot of promise, there are certainly areas for improvement. One limitation is that it inherits some of the drawbacks of behavior cloning. It can struggle if the demonstration data isn't adequate. There's also room for improvement in terms of computational efficiency. The inference process, while fast enough for real-time control, is still more computationally intensive than simpler methods.
Those are great points. Any final thoughts on the significance of this work?
I think this work is really exciting because it opens up new possibilities for robot learning. By leveraging the power of diffusion models, which have been so successful in other areas of AI for robot control, we're seeing significant improvements in performance and stability. This could lead to more capable and flexible robots that can handle a wider range of tasks in real-world environments.
Absolutely fascinating stuff, Eliza. Thank you so much for breaking it all down for us today. And thank you, listeners, for tuning in to another episode of ReLU Radio. Until next time, keep learning and stay curious.